Alrighty, so for our third and final video, we will be doing a bit of an extension on the principles of integration by parts. That's what this video is going to surround upon. Specifically, tabular integration is what we're going to be talking about, just to give you guys kind of a better way to go about doing your integration by parts when the problem you're doing involves a lot of repeated, when you're creating a lot of new integrals with each part of the problem. There are certain problems, like we're going to see, that where you're doing the process we discussed in the integration by parts video. If you try to do that for these types of problems, you're going to be doing, you're going to have just an infinite amount of just recursive style equations that are just, or expressions that are just created as you go through and do your math. So before we get into tabular integration, I just wanted to do something that was a little bit more sort of like a directly drawn from the last video, and that was going to be our our integration by parts. So we talked a lot about that in the second video, and so what we talked about in that video was mostly entirely surrounding integration of an indefinite nature, I suppose. So integration that it does not have boundaries. I'm not going to get too detailed into this, but I am going to give you guys the formula right now for integration that's defined for, so when you're doing integration by parts problems, if they give you boundaries, here's how you're going to do it. So you're going to plug it in to this formula right here. So integration by parts. So the formula for when it's definite, it looks like this. So the integral from a to b of u dv, and that's going to equal uv, and then that's going to be solved for the space from a to b. And then we're just going to subtract Alrighty, so here's how it's going to look for definite integrals. So when you're given a integral that involves an a and a b, so defined limits, and it looks like our udv, so our two separate types of expressions that are being multiplied together. So when we have an equation that u sub isn't going to work for, and it's defined, this is how we're going to handle it. It's very much the same as our integration by parts in terms of indefinite integrals. So the process for indefinite and definite is very much the same. It's almost exactly the same. The only difference is, instead of ending up with a specified equation, so like when you're not going to end up with an equation, you're going to end up with an exact answer, because this value is going to give you, this is going to represent an exact number right here. And then this is going to be something that you can solve either through further integration, whether it be more integration by parts, or you might have to u sub this again, or even tabular integration, which is what we're about to talk about. You might even have to use that again here. But no matter what you need to do, all you're going to be doing is adding that as a's and b's, and then when you pull u's or v's out of this integral here, you're just going to do your a and your b. You're going to solve it like you would any definite integral. And then at the end, you're also not going to involve a plus c. You're not going to have an exact integer answer plus c. It's not going to be how it goes. You're just going to be left with an exact integer number, although this is still going to be a measurement of space. So if you are given units, you're still going to need to put units squared at the end of these types of problems. But anyway, so that's definite integration. You should be able to figure out what this equation means based on the previous videos. So I'm not going to do any details like that just for the sake of time. So moving on to our tabular integration. So our tabular integration, it's really, like I was saying, it's an extension of integration by parts. So it's really just an easier, simplified way to do integration by parts. So, you know, it's not preferable to U-sub. U-substitution is still going to be more simple than this. This is the only time you should be using tabular integration, is when you have two expressions that are multiplied together. So your UDV. So when you have two expressions that are being integrated and multiplied together, you're looking at these both here in this integrand. You're looking at both these expressions. One of them should appear, if you're going to use tabular integration, one of them should be very easy to derive. Just looking at it, you should be good enough at derivatives and integrals by now to just look at whatever your u is, or whatever, you know, the two options for u, and see if anything looks like it's going to be easy to derive over and over again, because that's what we're doing with tabular integration, is repeated derivatives. So you're going to look at that, and if you're able to identify something, whatever it is in this integrand that's going to be easy to derive, you're just going to name that your u. That's how we're going to do that. And then you're going to have your dv. That's whatever's left that isn't your u. That's going to be ideally something that is very easy to integrate over and over again. That isn't going to cause, you know, some huge mess of, you know, chain rule created just complications. So your table isn't going to be as wide as the whole page. You want something that's going to be easy to derive here. Again, you can use, like we were saying in the integration by parts video, you can still use your Liate acronym here if it'll work. Now you have to be careful with this Liate. I think I mentioned this in the last video, but this acronym is not foolproof. There are exceptions to this rule. If this doesn't work, you can also try reversing your I and your L, which is most commonly the exception to the Liate rule that you're going to see. But if this doesn't work, you can also try switching these two around, and to make it ilate, if that makes it a little easier for you. But that's something you'll have to observe in practice. So we've chosen our u and we've chosen our dv, and tabular integration is it's going to be especially preferable. The one place where this is going to be really preferable is if you have a algebraic value, so like something that will eventually become zero if you derive it enough. That's what you're looking for. If you have that, and your dv is something that you can integrate over and over, because you're still gonna have to integrate that if you have x to the 5th ln of x, you're probably not going to want to use tabular integration for that, because integrating, you would have to use, that would be one exception, of course, to the rules. You would have to use ln of x as your u value in that case, because you can't derive ln of x easily. You're going to be dealing with sine over cosine, and canceling that out. It's going to be a mess. So it's really just about identifying which value is going to be your most useful u. Now, once you have both of those values and you've decided which is going to be which, you're just going to make a table right here. And this is how we're going to do this. This is tabular integration right here, a table right there in the name. Make a table, t-chart, whatever. And then under each of these, you're just, on this side, you're going to derive whatever the equation was. On this side, you're going to take the integral. So you'll just get r. And you're just going to keep doing that. You're going to keep doing that all the way down. So you're going to keep doing that. So you're going to be looking for one of two things when you're doing that. So if you're doing this, you'll do u double prime, and this will be integral of r. And then you'll keep going and going down, and your goal here, what you're looking for when you stop making rows in your table, you're either looking for one of these to go to 0, one of these will equal 0, so you'll have, that's one possibility, or you're looking for when this and this, so when your u derivative and your dv, when that stuff matches what was in your initial equation. So those are the two places where you're going to stop. Those are the two possible types of tabular integration that you can use. We're going to go through both of those. First, we're going to cover when the equation, or when the derivative or the integral goes to 0. We're going to talk about that first, and then we're going to talk about when neither of them will ever go to 0, and you're left with a recursive table that just seems to keep repeating itself infinitely. We will talk about how to deal with that as well. So let's just, without further ado, just hop on into those examples. So yeah, feel free to stop the video, take a picture, take notes. I don't know, I don't really write much stuff here in terms of taking notes, so you'll have to take your own if that's what you're trying to do here. So anyway, we're just going to move into our first example here. So our first example, it will just be the integral of x to the 5th. So that's going to be our first example. Go ahead and take a minute, see if you can figure this out, if you already know what tabular integration is, or if not, just keep watching and we'll get into solving it. Oh right, can't forget this. I always forget this. So when we're going to go into solving this, so the first step is of course going to be, identify, try to see if you can figure out why we're going to use tabular integration for this, because that's going to make it easier for you to start predicting what sort of methods you're going to need to use in solving your integrals. So try to think about why, not just how we're going to solve this with tabular integration, but why are we using tabular integration to solve this? And the reason is just because of this x to the 5th, which we know from our time with derivatives will eventually derive. If we keep deriving x to the 5th, we're eventually going to get 0, and that's what's going to make this feasible for us. So anyways, so here's the process for how we're going to actually go about doing this, and just make sure you pay close attention, because there's a lot of stuff to check out here. So we're looking for a u and a dv, essentially. We're looking for our u and our dv. That's the first thing we're doing here, so we can start our table. So we're gonna use our liate, so we can get into the habit of doing that. So liate, and of course, if you don't know already, this is logarithmic, inverse trig. This is algebraic functions, trigonometric, and exponential. So if you don't know what any of those are, just Google it real quick. But so we have x to the 5th here. That's going to be algebraic. That's going to be right here. And then we have sine of x, which is going to be trigonometric. So because liate is only used for finding your u value, we know that x to the 5th is going to be our u value. And like I was saying, liate is not perfect. Try to get into the habit of just forecasting ahead and not being fully dependent on liate to determine whether or not, or what your u value is going to be, rather. Don't be completely dependent on this. Try to think about it yourself before you result to this, because there will be instances, like I said, where this is not going to be applicable. It's not going to apply there. So so we know that our u is x to the 5th, and then our dv is going to be sine x dx. And then we're just going to make our little table. Like that. It's kind of like a T-chart. And then, so we're just going to start on in. Part of it is just filling out, the biggest part here is just filling out the table. This is exactly what you would be doing if you were doing integration by parts, which you could do for this function. It's just going to take all day long, because you're going to be writing out uv, and then this isn't going to fully integrate, so you're going to have to redo it over and over again. You're going to be using up an entire page worth of just scribbling math, algebraic nonsense, whereas, the table, we can just write out the table, draw it, and then get everything going easier. So we'll just start in by deriving this. So we're just going to derive u. So that'll just be 5x to the fourth, according to the power rule. And then we're just going to keep deriving it all the way down. And once again, derivative of that's going to be 60x squared. And then make another row. The derivative of this is going to be 120x. Make another row. And then below that, we're going to have just 120. And then finally, we're going to have our 0 all the way down here, because derivative of 120 is a constant, which is be 0. So that's going to be our derivative side. On this side, we're going to have to integrate this dv. We're going to have to integrate it over and over again, just like we derived this side. So the integral of sine x, because it's going to be negative cosine x, because the derivative of cosine is negative sine. So this will be negative cosine x. And then below negative cosine x, sine is derived into cosine, so this is going to be negative sine. And then below that, we have, this is going to be, when you integrate this, you're just going to get plain old cosine. Cosine derived as negative sine. And then we derive this cosine here. When we derive it, we're going to get just regular old sine x. And take the derivative of sine x. We're going to get negative cosine x, just like we did up here. Just like we saw up here, so it's going to be negative. And then down below that, since our 0 is right here, this is going to be our last row that we're going to be integrating. Derivative of negative cosine, it's going to be negative sine x. So now, as you can see, we have a table with a bunch of derivatives values and a bunch of integral values that we've taken from our initial function up here. Our initial integral up here is not a function. So we have all these values lined up here. So then, and this is where it gets very easy, because this is a 0 right here, we don't need to do, whenever you have a derivative that goes to 0, you don't need to do any further math beyond just plugging it in. And plugging it in is ridiculously easy for this stuff. So what you're going to do, and you're just going to come up to the top in your derivatives column on the left, and you're going to start with your very first number, your u value, your initial u value, and you're just going to start in this box and go across diagonally down there. And you're going to come down and do that again, and again, and again, and again, all the way down until you come to that 0 and you hit the last cross. You're just going to go down diagonal. That is how you're going to know which values are going to be multiplied by which ones to find your UD or your UV, because essentially what you're doing with tabular integration, because we had UdV and it was yes, we had UdV UV So essentially what we're doing here is, because we have a lot of instances where this is just going to repeat itself and we're just going to end up with a lot of repeated UVs in the end, right? If we did this with integration by parts, we would just end up with what are, in essence, a lot of repeated UVs in our answer. So what we've done now is just derive all these and then integrate all these, and now we have just a list of UVs, which are these diagonals here, that we can just multiply together and get we can get monomials that are parts of our answer, our final answer. So with this stuff, so then you're just going to start here, and what you're then going to do is, because of this negative right here, you have to factor this negative into your table. And so the way you factor in that negative, because the negative is a given, as a part of this equation. It's built into the equation. In order to incorporate it into your table, what you're going to do is you're going to take every other value of every second value in your u column, in your deriving column, and you're just going to make it negative. So u, and this one will be negative. Skip one, this one will be negative. 1, negative. So that's all you're going to do. Now you have 3 negative values, and those are going to cancel out with some of these negatives here, because the way it'll end up working out is you'll have negatives being created and taken out of here, so some of these negatives are going to cancel out. So if you make every other value negative, then you're going to start off, you will have a perfect set of negative values. Alrighty, so now that you've made your negatives, all you have to do is multiply, and you have your answer. So we're just going to multiply x to the 5th times negative cosine of x. So our first term is going to be, so this is just our answer right here, negative x to the 5th cosine x. Sure you guys can see there. Negative x to the 5th cosine x, and then we come back up to our table, and then we have a minus right here and a minus right here. So the sign in front of this is going to be a plus because they're going to cancel. So we have a plus 5x to the 4th sine x. And I might run out of space here, but that's okay. Plus 5x to the 4th sine x. And then over here we have a positive and a positive. So these are going to be, this one's going to be positive as well. So we have plus. And then we're going to go, 20x cubed cosine x. And then I'm just going to continue. This problem down here. So 20x cubed cosine x, and then we're going to come down to the next one, and we have a negative and a positive. So this one's actually going to be negative. So our next term is going to be negative 60x squared. And then sine x. And then we have this one right here, which is going to be positive negative, so we're left with another negative minus 120x cosine x. Alrighty. And then our final is just going to be positive 120 sine x, because these are going to cancel. Alrighty, and then at the very, very end here, we have to remember, because we solved an integral, we are now going to have to add our plus c. It's an indefinite integral, so we have to have our plus c. However, this is now going to be our answer in its entirety. It is very big and very ugly, and you would not want to be doing anything with this equation other than boxing it in as your answer. Now that said, that's how you get it with tabular integration. Imagine having done all these steps through the steps of integration by parts. It would have been arduous and taken forever. Instead, we have our table method here that is going to make it much easier for us. Righty. So tabular integration with no ending variable. So our example is going to be, let's see here, it's going to be derivative, or the integral of e to the x sine x. Alrighty, so this is going to be the problem we're doing, our last example for tabular integration. Alrighty, so we're going to start off doing this the same as we did our last problem for tabular integration. The process is essentially identical except for one key difference. So what we're going to do here is just put our liate on the page so we know kind of what we're doing here. Alrighty, so we have e to the x, which is going to be exponential, and then we have sine x, which is trig. So we have both of these identified on our Liate, so we know that our u value is then going to be sine of x. That means our dv is going to be e to the x. So that's our dv and that's our u, so we'll just put that down here. Okay, so then we're going to make our table like we normally do. And so our problem here is going to be, we got to start by integrating. So we're going to integrate this deriving rather, excuse me. We're going to derive this right side. So the derivative of sine x is just going to be cosine x. And then the derivative of cosine x is going to be negative sine of x. Alrighty, derive that. We're going to get negative cosine x. And finally derive that, we'll just get sine of x. And so then we're going to come over here and integrate this side. So e to the x, integral of e to the x, as we know, is just e to the x. And that's really just, it's going to stay exactly the same all the way down here. So by now you're probably noticing a pattern that we weren't seeing with the first tabular integration problem that we did. And that is, this will never, you can make an infinite number of rows to this table and it's never going to hit 0. That'll never happen. So when we have to solve equations like this, because I guarantee you, your teachers or your professors or whoever you're learning this for is going to one day give you a problem for which tabular integration will work, but it will not involve an algebraic component. It won't involve anything in your integrand that's going to eventually go to 0. It'll just be two different equations or two different types of equations like this that will just continue to produce just an infinite number of derivatives and integrals. So the way you're going to deal with this is, instead of looking for 0, you're going to change what you're looking for in your table. So instead of looking for a 0, what we're now looking for, we're looking for one row that has the exact same contents regardless of their sign, I need to emphasize that the sign of the contents is irrelevant for this. But we're looking for the row of our table that has exactly the same contents as our original derivative. So you can see right here, it's sine x e to the x. This is the first time that it repeats what's up in here. And as I was saying, this negative doesn't matter at all to us in terms of what we're trying to solve here. So now that we've seen this, we can just we can ignore all this stuff right here. Yeah, so we can just ignore all this stuff. All we need is down to here. So we're just going to rewrite our whole equation to make this next step a little easier to understand. So we have the integral of e to the x sine x. And that's going to equal, sine x, e to the x sine x. All right, and we have to do our crisscrosses, and we have to minus e to the x cosine x. And then we're just going to get minus and we're going to do e to the x sine x. So this is what we're now left with, and we have a good reason why, if you're doing this under the rules of tabular integration, as we've seen, This will just confuse the hell out of you. You won't be able to figure out what you're supposed to do here. But as you'll actually notice, this integrand and this integrand are exactly the same as we planned. So what you can actually do is just add this whole thing to both sides of the equation, and then this will just become 2 of this. You'll get, and then so then you bring it down here, e to the x sine x so you'll have this, and then you can just divide both sides by 2. And that is going to be your final answer. So I'll just rewrite it all up here for the final answer. So after dividing this all by 2, you're going to have your final answer is going to look like this: e to the x sine x minus e to the x cosine x, and the whole thing is going to be over 2, and you're going to add c on the end because you're solving an integral. And that is going to be your complete answer using excuse me, using tabular integration. This is how you solve your equations that do not end up as 0. All you have to do is keep doing your rows until you see the contents of both columns are matching what your original integrand was. Once you see that, you can start multiplying your diagonals together, and you can add your negatives in. And then you can just add over, down here, add over the repeated integral that occurs, and then you'll get 2 times that integral, and you can just divide by 2 on both sides, and that's how you get your answers. And then make sure you always add c at the end, because you can't forget that you're still solving integrals here. But yeah, that's pretty much it for tabular integration. I hope that ends up helping you guys out in the long run. But yeah, thank you so much for watching.